Great. So yeah, hi everyone. I'm happy to be here, and I'm also sorry that I couldn't be there in person. So today I want to talk a little bit about uncertainties in tipping warning and prediction. Sort of, there's already been a few talks about sort of, like early warning signals for tipping, and also sort of discussing options for that. And the sort of, yeah, the way I'm going to sort of introduce this is first of all just talk about uncertainties in general and sort of try to classify and understand them better, and then use the example of the AMOC and critical slowing down for the AMOC sort of warning of tipping, and then also sort of the prediction of a specific AMOC tipping time to sort of give you examples of how to look at uncertainties in these sort of like research questions. So first of all, I do want to say that this is going to be sort of about uncertainties in warning and prediction using critical slowing down, which you've already seen, I think, multiple times in this conference, and you probably all know about. It's the sort of way that the system sort of starts to be change statistically as it sort of approaches the bifurcation, which you can see happening down here in the animation, where the recovery rate from perturbations decreases. This is the negative recovery rate increasing. So the magnitude becomes smaller. But I think that like this way of thinking about uncertainties can apply also sort of to, more like physical early warning signals or other sort of like ways of trying to warn or predict of a tipping point. So the way I like to sort of think about this, and obviously there's a lot of sort of, yeah, there is a lot of like crossover between the categories, but I like to think of, first of all, this category of uncertainties that is the knowledge of the system. So all the assumptions that we need to make about the dynamical systems to sort of use our methods, even for something like critical slowing down, you need to assume that the system is sort of approximately in equilibrium while you're measuring it, right? So for the method to apply. And also then you have to assume something like the fact that the driving noise is non-white for some of these methods. And obviously, if you want to do something more precise, you need to make more assumptions. And then sort of we have the sort of other angle of this, where you're not actually like wrong, quote unquote, about the system, but it's a problem that we have very often in climate science, where we're not measuring the system exactly, right? So for example, for a lot of like Earth systems, we don't have like direct time series of exactly what's happening there. So for something like the Amazon forest or other vegetation systems, you need to use satellite data, which, as we saw from Lana's presentation, represents the actually what's happening with the vegetation to different extents. Then for something like the AMOC, you need to use sea surface temperatures or salinity. Generally for ocean circulation, we don't have long enough time series of what's happening at the ocean depth. And then for something like ice sheet height, you, for example, use melt rates that are derived from ice cores. So obviously, like in recent years, we have like more direct measurements of these systems, but if you want long enough time series, you generally need to use indirect proxies. The other sort of like uncertainty that comes from our sort of measurement of the Earth system is that we're not, we're not omniscient. Like we're not in every location at every point measuring everything, right? So like what you can see here on the right are salinity profile measurements from the EN4 data set, actually I think from 2001, so not even that long ago. But you can see that while there are a lot of like these clusters of profile measurements, they're sort of clustered around different areas, and there are these big white gaps. But then to sort of make this something usable, the data set basically sort of has these like pre-processing steps where these gaps are filled in using assumptions and other methods to give you this sort of like complete product which you download. And every like different data set has a different way to sort of fill in these gaps, a different way to correct for biases, to maybe smooth things down. And I would never want to imply that, this is like a problem. This, obviously the people who make these data sets are experts and they do their job really well. But the issue is that sometimes the sort of like focus of this sort of data set processing is to get the mean state correct, right? Because what we're most interested in is, how has the mean state of the ocean changed, for example, in the past like century or so. And then sometimes, that can be at the cost of accuracy in how the higher order statistics change. And when you're trying to understand how a stability of the system changes, for example, in a tipping element, you usually need to use something like higher order statistics or something that's a bit more sort of like detailed than what these data sets are optimized for. So what can we do? This is obviously, again, just sort of like my way of thinking about this. You can think of other examples. I think that the first sort of most obvious thing to do is to quantify the uncertainties. For example, these observational data sets that we download usually have their own uncertainty ensembles, which take care of some of the uncertainty estimates. You always need to be careful about like, what are these uncertainty ensembles actually quantifying? Because sometimes it might just be like one parameter and not the sort of whole uncertainty range that you're interested in. We can also sort of like develop methods or change our methods to account for some uncertainties. For example, the fact that the system isn't necessarily driven by white noise can be sort of like accounted for by, using a different method for calculating the restoring rate to sort of account for autocorrelated noise. I think the presentation after me, like Andreas, is going to talk more about things in that direction. And then there's also, the favorite method of all scientists, which is just arguing why the uncertainties don't matter and why you don't need to think about them. And obviously this can be very robust sometimes, like, for example, critical slowing down can also happen before non-catastrophic bifurcations, but these are, such the remote cases or unlikely cases that you could sort of argue, okay, we don't need to worry about that because it's very unlikely this is what's happening with the AMOC. And of course, you can combine things like do a little bit of quantification and then argue why that lets you ignore the rest of the uncertainties or something like that. So to move on to sort of the specific example that I want to talk about, which is the AMOC. We've already heard a lot about the AMOC today. And basically, I think probably a lot of you are familiar with Nicholas's paper from 2021, where he sort of identified this increase in the restoring rate in different AMOC fingerprints, which you can see here on the bottom row. The fingerprints are the top row, and also sort of identified these sort of patterns in the increase of the restoring rate, here the sort of red areas, which are sort of characteristic of AMOC transport, and so might indicate that the AMOC is losing stability. So the issue, sort of going back to this sort of like grouping of the measurement of the system, and today, I'm mostly going to be talking about this sort of right-hand side thing of like measurement of the system. I think we also have a lot of presentations in this conference which sort of fit this left-hand side as well. So all bases are covered. But going back to that sort of measurement problem, we have the fact that we don't have direct measurements of the AMOC transport, AMOC stream function before, continuous measurements before 2004. So we have to use fingerprints. For example, this is the most commonly used AMOC sort of proxy index, the AMOC SST index that I like to sort of abbreviate to ASSTI. So it was sort of defined by Lebke Caesar et al. In 2018. And basically, there are a lot of different sort of combinations for how you calculate this. But the basic idea is that you take the sea surface temperatures in the subpolar gyre minus the global mean sea surface temperatures, which you can see here from the ERSSTV5 dataset. And the sort of justification for using this fingerprint is that sort of if you look in CMIP6 models, and here I'm showing sort of historical CMIP6 runs for these sort of 27 different models for different ensemble members, you see that sort of overall the correlation of this sort of model ASSTI and the AMOC. Here, the y-axis is the AMOC at 35 north, and the x-axis, the AMOC at 26.5 north. The correlation is sort of overall pretty good. Obviously, there's the scatter amongst models. Some of them are not well in some of them, the AMOC is not well represented by this fingerprint, but sort of overall, this correlation is above like 0.5. But obviously, there's this issue here that 0.5 above 0.5 correlation is still not, a 100% correlation. So you still have a big part of this ASSTI fingerprint isn't directly related to the AMOC. So you can ask basically this increase that you see here in the restoring rate in this fingerprint, could that be connected to some other physical change going on? right? Like, could it be something like the atmospheric effects changing this higher order statistics? Could it be that like basically ocean memory is changing all over the ocean, and a bit that way increasing the restoring rate? Or could it be that maybe this sort of change in the subpolar gyre sea surface temperatures just indicates a subpolar gyre collapse and not an AMOC collapse, where you see here, this is from a CMIP5 model, where the blue line is a subpolar gyre collapsing and the AMOC stays strong. So the way we sort of like checked for, I like to call these like physical false warnings, basically, right? Because it's the warning isn't about the AMOC, but it's not about the AMOC because of a physical reason. Sorry. Basically, we take these CMIP6 models that I showed you before, the historical ones. So we have 133 sort of ensemble members in total from these different models, and we calculate different critical slowing down indicators for each of these, so restoring rate, AR1 variance, and then for each of these, we calculate the trend, and then we also sort of use Fourier surrogates to get a significance for that trend, right? Like, given sort of the statistical properties of this time series, how likely is it that you have this sort of increase in the restoring rate? And then, for example, for this one, you get a significant value, 0.02. But then we sort of cap this p-value at 0.05, right? We say that this is a significant increase if the p-value is smaller than 0.05. But that means that we have 133 time series, even if all of them are completely random and none have like a sort of really sort of physically caused restoring rate increase, just sort of randomly. When you sort of have this 0.05 p-value sort of cap, then you still get like 7 time series, even if everything is completely random, right? So sort of to have true significance out of these 133, you need more than 7 time series to have a p-value smaller than 0.05. But actually what we see in CMIP6 is that sort of now this black line is the expected value, and the important part in this slide is just to look at the pink, which is sort of the number of significant increases for the ASSTI, CMIP6 historical runs. And you can see that for the autocorrelation and variance, it's about the expected value. And then for the restoring rate, it's sort of even less than the expected value. And for sort of the stream function, which is the other colors, it's a bit more. That's sort of a more complicated question. If you're interested, you can have a look at our paper to see a discussion of that. But sort of the important consequence that I want to get to here is that all these other physical effects that I was talking about before, like ocean memory loss or atmospheric effects, they're all still there in the historical run in CMIP6, right? But we don't see any sort of like restoring rate increases. We see what we expect statistically. So sort of, at least from these results, we can say that this fingerprint isn't prone to these physical false positives, right? There's no like, if we see a restoring rate increase in this fingerprint, that's actually a very surprising thing, because in CMIP6, we don't see it. So now going on to this like other sort of like measurement uncertainties, which comes from these observational data sets. We're here for this fingerprint specifically, it's the sea surface temperature data sets. The reason, like I said before, that we might be worried is because what you see here is on the left is the number of sea surface temperature observations since 1850. And you can see that they've increased exponentially. So really huge increase. And then also, if you look at sort of where they're concentrated in the ocean, here on the right, it's sort of like the density of these observations in the data set. You can see that they're very much clustered around the coast and a bit more in the sort of like Northern Atlantic and less in the south. So you can imagine that when you sort of like process these and fill things in, this might cause problems for the higher order statistics. Obviously, that's just a hypothesis. So we test this in 2 different ways, sort of going back to that what do we do question that I answered at the start. The first thing that we do is use these sort of uncertainty estimates that come with the sea surface temperature data sets. Not all of them have that, but we use that. And we also use multiple data sets always. And the second thing that we do is that when we generate these surrogates to estimate the significance of the trends, we incorporate the data processing into the surrogates. So if there's like gaps in the data that are sort of infilled in a specific way, you can incorporate that infilling into the way you generate the surrogates. And then your significant estimate is sort of significance given the data processing already. I'm sort of mostly going to be showing things for the first point here, just in the interest of time. But again, you can have a look at the paper if you're interested. So if we now look at this sort of AMOC ASSDI index, AMOC fingerprint, in 3 different SST data sets, here you can see the black is sort of like the fingerprint, and then in green you have the uncertainty ensemble range around it, given these uncertainty ensembles that come with the data sets. And you can see that different data sets have different fingerprints a bit, and also different sort of like uncertainty ensembles, given the way that they process the data. And so now we calculate the restoring rate for each of these sort of like uncertainty ensemble members, and we get this range also around the restoring rate. And you can already see that this sort of like increase is now not as stark, perhaps, in some of these sort of like time series in the ensemble range. But of course, we do the next step and we calculate the trends of each of these sort of like restoring rate time series, and you get a distribution of trends, which is positive in all of the data sets, but in some of them it is more sort of densely clustered, in some of them it's a wider distribution. And then the last step is, like I said before, calculating the statistical significance of each of these increases, right? Is it a significant increase? And so we have the p-value for each of the slopes. And you can see that sort of like, again, our sort of value for sort of significance is this 0.05 here in gray, but like you could also, I guess, put it at 0.1. More interesting is to look at, like how these p-values are clustered. You can see that in HAD-SSD4, almost all of them are below 0.05, but in the other data sets, also more than half of the p-values are below 0.05, and also most of the other ones are below 0.1. So this like gives us an idea that, okay, while not all of the ensemble members have sort of like the same significance or like large increase, they're still sort of like all relatively significant or relatively sort of like strong increases. So the other way to look at this, as I showed that Nicholas did in 2021, is to look at this sort of like grid cell by grid cell. Right, so we calculate the restoring rate for each grid cell. You see this sort of like red areas are sort of in areas characteristic of the AMOC. And again, we can calculate this for each ensemble member, taking a lot of computational time. And then we can get these sort of like regions where basically these colored in sort of green regions are where most like more than 95% of the ensemble members have a positive trend. So these are the ones where like even when we look at the uncertainties, you still sort of see this increase in restoring rate. And you can see that these areas are still the areas that are sort of characteristic of AMOC transport. So I can't go into like more of the other things we did in this analysis, but you can have a look at the paper. The sort of conclusion that we had was that critical slowing down in these sort of like sea surface temperature and salinity based sort of AMOC fingerprints, it's still present and significant when you account for these uncertainties. It might be a little bit less significant than just in the sort of data without the uncertainty, but it's still there. Now, the issue comes a bit more when we want to do tipping time prediction. Like I said before, this sort of like these uncertainties can affect different methods and different processes in different ways because you also make different assumptions. And the methods have different sensitivity. Because of course, like when you do this sort of critical slowing down analysis, the first thing that like you really want to sort of answer is like, when will the AMOC actually tip, right? Like, can you actually extend this analysis into the future and answer the question that like, every time that I talk to like, a friend or a journalist or someone, that's what they always ask, when will the AMOC tip? The issue is that we still have all of these uncertainties that I described before here, but also prediction is a lot more sensitive than warning, right? Because you can imagine, for example, that like, as long as we have a significant slope here, we can say the AMOC has been losing stability in the historical period. But if you sort of want to like find where some sort of like extrapolation hit some sort of line, then the slope, just little changes in the slope can really impact what happens. And basically the way we sort of like test this for the uncertainties for the AMOC is by using the method developed by Ditlevsen and Ditlevsen in 2023. It's a maximum likelihood prediction method, also based on sort of like these historical data sets and fingerprints, and we sort of look at the different uncertainties for these. So the first sort of more general way that we do this, which is just using this maximum likelihood estimation method, but not specifically for the AMOC, is that we have a look at what modeling assumptions this method needs to work. And so this method, first of all, assumes that the system can tip. Any method that predicts tipping is going to assume the system can tip. Then you have the assumption that the sort of system is well represented by a full normal form bifurcation. The third assumption is that the system is driven by white noise, so not, for example, autocorrelated noise. And the fourth assumption is that the change in the forcing is linear. It's been linearly changing in the past and will continue to do so in the future. And sort of we have this toy model where all of these modeling assumptions hold. So it's a full normal form with white noise and linear forcing. And we sort of run that a few times and we get these sort of like time series. And then we apply this maximum likelihood estimation method to that and see what we get. And you can see that sort of when the assumptions hold, the method works quite well. This sort of like distribution is peaked around the true tipping time here in the dashed black line. So it's not perfect, but it works pretty well when the assumptions hold. The issue is, okay, what happens if we break some of these assumptions? So now we're going crazy and we're breaking all of the assumptions and like seeing what does the method do when we have a linear model with red noise forcing, right? Like a system that like can't even tip. Well, because this method is built to predict tipping, it still predicts a tipping time. Right? It's sort of like it predicts the tipping time, even though there's no dashed black line here because our toy model can't tip at all. It's a linear model. But you might say that this is too extreme because, the AMOC, like we are assuming that the AMOC can tip just by sort of like doing this research project. So what if we just break the sort of like white noise forcing assumption? Well, then you get a sort of bias to earlier years from this method, right? Because if we force it with a red noise with changing autocorrelation, the method sort of doesn't really know that that's what's going on, and it predicts a tipping time here with a sort of bias earlier than this dashed black line, which is the true tipping time. And the same thing happens if we have a forcing that is slowing down and not linear. And this, you can easily imagine that this might be true for the AMOC because just because sort of the AMOC is forced by something like, freshwater forcing, we're not exactly sure how that's going to change in the future. And it's not, far out of the like reasonable to expect it not to change linearly. So you can see that, again, you have this bias to earlier years in this prediction. And also we can have a look at like, what if the model is not a full normal form? Here specifically for the AMOC, what if our toy model is a 2D Stommel-Sessi model? And here sort of this method predicts a bias again to earlier years if you assume that it's a full normal form and apply it to a Stommel-Sessi model. So this is sort of like already a proof of concept of why these uncertainties matter so much when you're trying to make a prediction. But we can also do a sort of more sort of, practical result with the sort of measurement uncertainties, where basically we have, first of all, the issue with the fingerprints not representing the AMOC directly and also the SST datasets. So what we do here is very simple. We just use a few different SST fingerprints because they all represents the AMOC not 100%, but in different ways, not 100%, right? So we have this sort of classical subpolygia SSTs minus global mean SSTs that I was talking about before, but we also use the one that Ditlevsen and Ditlevsen et al. Use, which is minus 2 times global mean SSTs, sort of to account for Arctic amplification, I think. And then you have the dipole fingerprint, which you have northern box SSTs minus southern box SSTs. And these obviously are all fingerprints that are commonly used to represent the AMOC. And then we've already seen this extensively. We use these 3 different SST data sets, HED-ISSTI, HED-CRUD5, and ERSSTV5. You can already see in this is sort of the plot of like restoring rate increases. You can see that the patterns are slightly different. So you can imagine that there might be differences in what happens when we try to use this to predict an AMOC tipping time. And so when we use the same data set that Ditlevsen and Ditlevsen et al. Use, which is HED-ISST1, for these sort of 3 AMOC fingerprints, you can see that the predicted tipping times are sort of clustered around here, around sort of the 21st century, between like 2050 around and like 2100. But from how I've sort of drawn this x-axis, you can already imagine what happens when I sort of like, when we apply this method to other data sets and fingerprints, we get this sort of like range in predicted tipping times, right? For HEADCRUD5, you get predicted tipping times up to 3,000. And then for ERSSD5, you get predicted tipping times going up to the 50th century. And similarly to what we did for the sort of like just critical slowing down, we could also look at the uncertainty ranges, right? HEADCRUD5, has a 200 member uncertainty range ensemble, and we can sort of like apply this sort of like method for predicting a tipping time to each of the members, and you get this distribution where for the dipole fingerprint, the sort of like top of this distribution is actually around 8,000. So you see that already in this figure, the situation is more complicated. And you also need to remember that like in these sort of SST data sets, you can't say that one of them is better than the other, right? They're all sort of like commonly used, robust and trusted SST data sets. So basically, when we have these uncertainties in tipping time prediction, because the method is so much more sensitive, we don't really get a practical result. Like there's nothing wrong with this spread, but if you want to know when will the AMOC tip and the answer is sometime between 2000 and 5000, that doesn't really help you a lot. So in conclusion, I hope that I've sort of showed you why we really should be considering uncertainties when we try to warn or predict tipping points, especially if we're using historical data and we're using higher order statistics in historical data. But that sort of, if we just want to warn of the collapse, say something like the AMOC has been losing stability, then sort of we can still sort of account for these uncertainties, for example, by showing that the SST fingerprint isn't prone to physical false positives, or that you can sort of account for the dataset uncertainties and show that like the critical slowing down is still significant in subpolar North Atlantic SSTs. But if you want to do something more sensitive, like predict an exact tipping time, then the uncertainties are too large if you're using historical data. So yeah, thank you. And if you want to have a look at any of our papers, you can use these QR codes here. But I think I'll stop sharing now because we're moving to the Q&A, right?